Talk about gas laws, and what we want to be able to do at the end of this is just be able to make any kind of calculation involving gases and the different properties of gases. So the first gas law we're going to talk about is called Boyle's law. Now, Boyle's law relates the pressure and the volume of a gas to each other. We're assuming here that the temperature and the amount of the gas is remaining constant. So the relationship to know here is that as the volume decreases, the pressure increases. So we have what's called an indirect relationship between pressure and volume. You can see here in this picture that as the container got smaller, the particles were bouncing around more. Now remember that pressure is also a measure of the number of collisions that these particles are making. So if there's a tighter space for them to move around, obviously there's going to be more collisions, hence a higher pressure. Now the equation for Boyle's law follows as P1V1 equals P2V2. The initial pressure and volume is equal to the final pressure and volume. Okay, so let's look at an example of when this would be used. A balloon contains 30 liters of helium gas at 101 kilopascals. What is the volume of helium when the balloon rises to an altitude where the pressure is only 25 kPa? So knowing our Boyle's law, we have P1V1 equals P2V2. All right, so the hardest part is just identifying what these numbers actually mean. So we have 30 liters. Liters indicates that's a volume of helium gas at 103 kPa. The kilopascals is the unit for pressure. So we have an initial volume and pressure, hence your P1V1. So 103 times 30. We are asked to find what the volume of the helium is going to be. Okay, so we're looking for a V2 when the pressure of the balloon drops to 25 kPa. So equals your P2 is 25 and we are looking for V2. So we get 103 times 30 divided by 25 equals your V2. So your volume should equal around 123.6 liters. This makes sense because of the fact you see the pressure dropped from 103 to 25, which is a decrease in P. So if the pressure decreased, the volume should have increased. They have an indirect relationship. The volume went from 130 to 123, which makes sense if the pressure decreases as well. Alright, so let's take a look at another gas law called Charles' law. Now, Charles' law relates together the temperature and the volume of a gas. Alright, so now we're going to assume that there's constant pressure, and again, the amount of gas is remaining the same. So the relationship here is that as the temperature increases, so does the volume. Okay, so as you increase the temperature, things tend to expand. Okay, so there's what's called a direct relationship between temperature and volume. Alright, so just imagine if you were to heat up a gas, that gas would begin to expand outward. So the equation we use here for Charles' law is V1 over T1 equals V2 over T2. Again, we have that 1 is the initial and 2 is the final. So now let's take a look at an equation, a question. Okay, once again, we're inflating a balloon in a room where the temperature is 24 degrees and the balloon has a volume of 4 liters. The balloon is then heated to a temperature of 58 degrees. What is the new volume of the balloon? So here we're given a temperature and a volume, which should call to mind Charles' law, V1 T1 equals V2 T2. Right. So our initial volume, 4 liters, and our initial temperature, 24 degrees centigrade. And we are asked what is the new volume. So we're looking for V2 when the temperature rises up to 58 degrees. Okay, so just doing a little bit of algebra here, you get that V2, your final volume, is equal to 9.66 liters. Okay. Once again, your temperature started at 24, increased to 58. Okay, so you have an increase in the temperature. And we said that as the temperature increases, so does the volume. The volume went from 4 to 9.66, which also indicates an increase in the volume. So that's a good way to check that we actually did this right. They should follow the same exact kind of trend. Moving on to our next law, Gay-Lussac's law. This relates together the pressure and the temperature. Now we're assuming that the volume and once again the amount of gas is remaining constant. So as the temperature increases, so does the pressure. Again, whenever we talk about pressure, we're usually talking about the number of collisions. So as we're making things hotter, providing more energy, the particles tend to move faster and thus they collide faster and stronger with each other. So more collisions, hence an increase in pressure. So this equation looks similar to Charles' law, but rather than having volume, we have pressure here. So we have P1 over T1 equals P2 over T2. So let's take a look at a question here relating Gay-Lussac's law. So the aerosol cans that we have at home, just like sprays and stuff like that, they usually have labels on them that warn you about incinerating them, burning them, or keeping them above certain temperatures. And that is because they actually tend to explode. So if the gas in a used aerosol can has a pressure of 103 kPa at 25 degrees, which is room temperature, okay, if you throw that can into a fire, what will the pressure be when the temperature reaches 928 degrees centigrade? All right, so we've got our P1 over T1 equals P2 over T2. All right, so our initial pressure and temperature, 103 over 25. We're looking for that new pressure. Okay, so we're looking for a P2. And we know that the temperature is going to increase to 928. All right, so solving for P2 gets us a pressure of 3,823.36 kPa, which is massive. This is why it's so dangerous to throw these cans into a fire, because you can see the pressure of that gas in the can is really, really high, which is why they tend to explode and it can be pretty dangerous. And once again, you can see this pattern that the temperature increased, so the pressure should have as well, because they have that exact same relationship. Our final gas law here is called the combined gas law. As you can imagine from the name, it just combines the other gas laws together. So it describes the relationship between pressure, temperature, and volume. And you can use this for any situation where only the amount of gas is staying the same. Okay, so everything else changes except for the amount of the gas. And one of the cool things about the combined gas law is that if you hold fixed one of the factors or one of the variables, you can actually derive the other gas laws for it. For example, if the temperature is constant, you ignore the T's here and you get Boyle's law, P1 V1 equals to P2 V2, where temperature is constant. Okay, so this combined gas law just takes the other gas laws and puts them together. Okay, so a question involving the combined gas law would once again be a balloon where the volume is 30 liters at a temperature of 313 Kelvin and a pressure of 153 kilopascals. We want to know the volume at STP, standard temperature and pressure. Okay, so our combined gas law, P1 V1 over T1 equals P2 V2 over T2. All right, so we have our initial pressure, volume, and temperature. Okay, so we have a pressure of 153, initial volume of 30, and an initial temperature of 313. Now, STP means that the temperature is equal to 273 Kelvin, and the pressure is equal to 1 atmosphere, which in turn is equal to 101.3 kPa. All right, so STP is a set condition. This is what the temperature and pressure equal. All right, so we need to find what the volume is going to be. So we know the pressure is going to be 101.3. We are looking for the new volume, and we know that the temperature is going to be 273. Okay, so if we're just going to go ahead and chip away to solve at V2, multiplied by 273 on both sides. Okay, so you get 273 times 153 times 30 divided by 313 equals to 101.3 V2. All right, so now we're going to divide by 101.3 on both sides. So numerator starts to look like 153 times 273 times 30 divided by 101.3 times 313. So this is just like a super put together way to kind of solve for it. You're welcome to solve for however you like. You get V2, which in the end ends up equaling 39.5 liters. Okay. Well, there you have it. These are all the different gas laws that are present depending on the factors that are either held constant or changing. So with these, you can actually calculate several properties of gases.